Hey everybody. Today we're talking about empirical, classical, and subjective probability. Basically, there's multiple things we might be talking about when we're talking about probability, and so we want to get a better handle on the differences between them. Empirical probability, sometimes called statistical probability, is based on observation. So when a probability experiment is conducted repeatedly, we define the empirical probability of an event to be the number of times the event occurred divided by the total number of trials. So a couple examples of this. A coin comes up heads 53 times in 100 flips. So the empirical probability of a head is 53%, 53 over 100. Even though intuitively you might be thinking it should be 50%, that is not empirical probability. Another example. In a poll of 750 randomly selected pet owners, 412 prefer dogs to cats. So the empirical probability that a pet owner prefers dogs to cats is 412 over 750, about 54.9%. Classical probability, also known as theoretical probability, applies when all the outcomes in a sample space are equally likely. And in that case, you can get the classical probability by counting the number of outcomes in both the event and in the sample space and taking their ratio. So for instance, if you roll a fair die, there's 6 possible outcomes. So the size of the sample space is 6, that's the denominator. And there's just one outcome in the event E, when you actually roll the 5. So the classical probability of the 5 is 1 in 6. A slightly more involved example, a fair coin is flipped 3 times. Let's find the classical probability of the event of getting exactly 2 heads. So this is a good place to pause the video, write down the sample space, the event, and find that classical probability. So the sample space has 8 possible outcomes in it, things like heads, 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 and heads, heads, tails. And all of these are equally likely because we have a fair coin. The event of getting exactly 2 heads has 3 outcomes in it. We can have the third one be a tail and the other 2 heads, the second one be a tail and the other 2 heads, or the first one be a tail. So the classical probability of the event E is 3/8. The numerator, 3, is the size of the event E, the number of outcomes in E, while the denominator is going to be the number of outcomes in S. Another slightly different example. Consider the following frequency distribution for an introductory statistics class at a large university. What's the probability that a randomly selected student in this class is a sophomore? So again, pause the video. Think about not just the answer to this question, but also whether this is classical or empirical probability. So since we are taking one of the students from this class, this is classical probability. There are 222 students, all of whom have an equally likely chance of being selected. There are 72 sophomores in here, so the probability of getting a sophomore randomly is going to be computed using classical probability, 72 over 222, about 32.4%. Related example, what's the probability that the next person who registers for the course will be a junior? So again, good place to pause the video. In this case, we're talking about empirical probability. We've observed 29 juniors out of 222 total students, so the probability that the next one will be a junior is 29 divided by 222. This is a situation where we're not just taking one of the 222 students at random, each being equally likely. Rather, we're using our experience to create this ratio. Although notice that the actual calculation looks pretty much identical, right? It's the sort of number of good outcomes on the top and the total number of possible outcomes on the bottom. Regardless of which sort of probability we're talking about, a few things should always be the same. To start, the probability of any event is always between 0 and 1, with 0 being an impossible event, something that can't happen, and a probability of 1 being a certainty. To say that latter thing slightly differently, we say P of S is 1, where S is the sample space. And this is just saying that when you run a probability experiment, something has to happen. One of the outcomes has to occur. Finally, if E and F are both events and they're disjoint, then the probability of E or F is the sum of the individual probabilities of E and F. Additionally, of course, since they're disjoint, the probability of both of them occurring is 0. Finally, In our everyday lives, we often just use the language of probability loosely. We estimate the chances that something will happen just based on intuition and general life experience. In statistics, we refer to this as subjective probability. A couple examples: I'm 99% certain that I'll win this game. There's a 50-50 chance that my phone will die today. And these statements are descriptive and sometimes useful, but they don't have mathematical meaning, and I wouldn't try and do any sort of calculation with any of these. So, for instance, when I say that I'm 99% certain that I'll win the game, that might be based on experience, but it's not like I've played a million games and counted how many times I've won, taken a ratio, and found it to be 99%.